Here, let's extend our integration by parts formula to definite integration. So in other words, if I'm integrating from a to b of f of x g prime of x, well, our integration by parts formula would be f of x g of x. In this case, now we're evaluating it from a to b, minus the integral f prime of x g of x. And this one again evaluated from a to b. So we're just adding in this evaluation step. So similarly, if I have it in the other formula, u times dv, integral from a to b will be uv evaluated from a to b minus the integral from a to b of v du. So let's practice this with an example. Here we've got the integral from 0 to 1 of tan inverse. So it may not be obvious here that we want to use parts to solve this. So why is it that we would be able to use parts in this case? Well, the reason is because if I choose u equal to tan inverse of x, then when we take the derivative, it transforms this into an algebraic expression. And so once it's expressed as an algebraic expression, then perhaps its integral may be more obvious, or its antiderivative may be more obvious. So in this case, the u will be tan inverse. The dv will be dx. So the du will be 1 over the square root of, 1 over 1 plus x squared for tan inverse. And the v will be x. Now the parts formula again will be u times v, so x times tan inverse x. And in this case, evaluating from 0 to 1, minus the integral from 0 to 1 of v times du, which will be x over 1 plus x squared. Okay. In this case, now we can evaluate x tan inverse of x from 0 to 1. So that will be 1 times tan inverse of 1 minus 0 times tan inverse of 0, which of course is just 0. Now let's think about how we're going to integrate this remaining expression, x over 1 plus x squared. Now in this case, my thought is to now just do a normal substitution. Typically we can look for substituting when we have in this case, the derivative of 1 plus x squared is a multiple of x, which we have up here. So here I'm going to call this u, but it's a different u than we're using here, right? So let u equal to 1 plus x squared, and du will be 2x dx. So this is now just going back to our typical substitution. So we have 1/2 du is x dx. So after substituting, this integral transforms into 1/2 1 over u du. I should also change my limits of integration as well, since it was originally from 0 to 1. So let me write down here, when x is 0, u will be 1 plus 0 squared, so it'll be 1. And when x is 1, u will be 1 plus 1 squared, so it'll be 2. So my new limits of integration go from 1 to 2. So let's finish it up here. We've got the 1 times tan inverse of 1. We remember tan inverse of 1 is pi over 4. Tan inverse of 0 is 0, so of course it's times 0 as well. And here we'll have 1/2 integral from 1 to 2 of 1 over u du. So that'll be 1/2 ln of u. evaluated from 1 to 2. So that'll be pi over 4 minus 1/2 ln of 2 minus ln of 1. Remember, ln of 1 is 0, so we're just left with pi over 4 minus 1/2 ln of 2. So there we have it. One last thing I could actually do here is I could bring the 1/2 in as a power of 2 and write that as the square root of 2. Okay, so you can leave it like that. And here in this next example, we're going to go through the proof of a reduction formula. And this will kind of lead nicely into the next section where we explore these kind of trig functions more carefully. But what does this reduction formula do? If you notice, what it does is it takes some power of sine. Here, my assumption is that n is greater than or equal to 2 and is an integer. And so, for instance, if I have sine raised to the power of n, it allows me to rewrite this as an integral of sine to the power of n minus 2. So it reduces the power of this sine function by 2. And in most cases, if I have a very large power of n, we might have to apply this formula many times to reduce it completely. But let's just walk through and show how this formula can come about. And it's going to use a couple of strategies that are sort of key to what we're going to see in the next section, but also some strategies that we've already seen in this section when we're applying the integration by parts formula. So the first trick is to start with the left-hand side, where I've got sine to the nx, and I'm going to split off one factor of n, or sorry, one factor of sine. So it's going to reduce the power of sine to the n by 1 here, so it becomes sine to the n minus 1 times sine x. Okay. And then, after I've split it up like this, I'm going to do parts. Okay. And the way I'm choosing the parts here, this will be my u, and this will be my dv. Okay, so if I let u equal to sine to the n minus 1, and then my dv will be sine x dx. I get du here will be taking the derivative of sine to the n minus 1, so that'll be n minus 1 sine to the n minus 2 times the derivative of sine, which is the inside function, so times cosine x. Okay, so that gives me my du. And v here would be the antiderivative of sine, which would be negative cosine. So after I've figured out what my u and my dv are, well, let's write out what the integration by parts formula gives us. Okay, so that'll be u times v, so that'll be sine to the n minus 1 times negative cosine. So I'll write negative cosine x sine to the n minus 1. So it's the uv minus the integral of v du. So here we've got v is negative cosine x times du is all this stuff here. So a couple things I noticed for the n minus 1, that's a constant. I can take that in front of the integral. I can also take the minus sign out, so it becomes plus n minus 1. I'll multiply cosine times cosine, so we get cosine squared. And then we have sine to the n minus 2. Now in the next step, what I want to do is try and manipulate this integral a little bit. Okay, and we'll see this is going to be a useful trick maybe in some cases where if I've got sine with cosine squared in it, I can try and rewrite cosine squared as 1 minus sine squared. Remember, this is just a fundamental identity. Right? Sine squared plus cosine squared equals 1. So cosine squared is equal to 1 minus sine squared. So let's see what we have now. So we got 1 minus sine squared times sine to the n minus 2. Now when I distribute sine to the n minus 2 into the parentheses here, let's see what we get. So that gives me the integral of sine to the n minus 2 minus sine squared times sine to the n minus 2. We'll add the powers there and we just get sine to the n. Now what I'll do is I'll distribute the n minus 1 to each of these terms separately so that I can split them into two separate integrals. Because then I notice that the integral of sine to the n is really the integral that we started with. And that kind of reminds me of a trick that we saw earlier. So we'll see if that same trick works here. Okay, and so there we have it. We see that this is the same integral that we started with. So let me kind of rewrite that over here to remind ourselves that now if I want to combine, if I want to isolate this integral, I can just add it to both sides of the equation. In this case, I'm going to add n minus 1 times the integral of sine to the n to both sides. Okay, and in doing so, well, here it's like I'm adding 1 plus n minus 1. So combining those gives me n times the integral. And then what remains over here would be negative cosine x sine to the n minus 1x plus n minus 1 times the integral of sine to the n minus 2 x dx. And then one last step to go gives us the result that we wanted. All right, so if I divide the n here in the next step, then you notice that'll bring us to the final step that gives us our formula. So that would be the one last step here. I'll just write it out. So dividing n to both sides. So here you can imagine I'm dividing n to both sides. So I'm going to divide each of these terms by n. Gives me my final result. The integral of sine to the n x dx equals negative 1 over n cosine x sine to the n minus 1 plus n minus 1 over n, the integral of sine to the n minus 2. Okay. There we have it. So in improving this formula, we got to see a couple of very useful techniques in action. So don't feel overwhelmed like if you couldn't figure out how to do this on your own, because that's not the point. You're not expected to be able to prove these things out of thin air. But hopefully you were able to follow along with each of the different steps that I did here. Even if maybe you couldn't have figured out those techniques or those little tricks on your own, it's okay. The key thing is that you're able to follow along as I go from one step to the next and figure out why I was doing each of those tricks and how each of those tricks helped. For instance, here, the first thing I did was I split up those two terms, or those two factors, so I split off one factor of sine so that I could apply parts. Another trick was here, I rewrote cosine squared as 1 minus sine squared. And then that trick that we saw earlier was when we wound up with the same integral that we started with at the beginning, we were able to isolate that integral in the equation, sort of solving it algebraically. And so each of those little tricks that we did was a very useful part of the puzzle. Okay, so we'll leave it there for this problem.